So in this session, we will talk about comparison tests. So before we begin, let us recall the things that we've known so far. We have the definition. So the series sum an from 1 up to plus infinity converges if its sequence of partial sum is convergent. Otherwise, the series diverges. So again, let me recall this sequence of partial sums. So Sk, this is the sum of the first k terms of the series. And then we also learned the divergence test. So if the limit of the terms an as n approaches infinity is not equal to 0, then the series an is divergent. Okay? So the divergence test. If the limit of an as n approaches infinity is not equal to 0, the series is divergent. Now, once again, I remind you that if the limit of the terms as n approaches infinity is equal to 0, we cannot conclude anything. Okay? So the series may converge or the series may diverge. So we have to use other methods to identify if the series is convergent or divergent. And then last time we learned integral tests. So for the integral test, suppose we have a series an, okay, with non-negative terms. And suppose we have a function f that is continuous, positive, and decreasing on the interval 1 comma plus infinity. Okay, and the evaluation of the function at each natural number n is equal to the term a sub n. Then the series converges if the improper integral of f of x dx from 1 up to plus infinity converges, or the series diverges if the improper integral also diverges. And in here, take note that for this part, the interval here, we said that it's from 1 to plus infinity. We can replace this to the interval k up to plus infinity for some k here, k greater than or equal to 1, whatever your k is. So you can check if the function is continuous, positive, decreasing on this interval. And of course, this guy here, it will change. You can start with the integer equal or greater than k. Okay, not just for all n. You can start with the number with the integer greater than or equal to k. Okay, and of course, if you compute the improper integral, these guys here will also change to k. Okay, so we can do that for the integral test. So now we will learn the next techniques. We call them the comparison tests. So how do we do that, and what is this comparison test? We know that this guy here is convergent because it's a p series with p equals 2. And in fact, we solved this 1 over n squared before. We said that this guy here, it's actually equal to 2. We found that. Okay? So the question is, what about this series here? What about the series 1 over n squared plus 1 as n runs from 1 up to plus infinity? Now, take note that for all n, you have this inequality. 1 over n squared plus 1 less than 1 over n squared. If you don't see that, um, you can start with the following. You have for all n, n squared, it's less than n squared plus 1. So of course, if you do the reciprocal, the inequality will change. That's why you will have this inequality. And of course, in here, these are all positive. Okay? This 1 over n squared plus 1 for any n, for any natural number n, it's always positive. Okay? So now, suppose we let S sub k, small s sub k and capital S sub k to be the sequence of partial sums of these two guys here, respectively. Okay? So you get the partial sums. For this, you will denote that by small s sub k. You get the partial sums for this, you will denote that by capital S sub k. Okay? Then, clearly, small s sub k will be less than capital S sub k. Because for each term, this guy here, it's smaller than this guy. So even if you added the first k terms with this form, it will still be smaller than the sum of the first k terms for this form. That's why you have this small s sub k less than capital S sub k. And again, these two guys here, they are positive. Okay? So, if we get everything, okay, if we get everything, S sub k, it's positive and it is increasing. Okay? This is increasing. Now, we know that capital S sub k, this sequence here, it is convergent. Correct? It is convergent. It's this guy here because it's a P series. So the limit of S sub k here, limit of capital S sub k as k approaches plus infinity, this is equal to sum S. In fact, we found it. Let me write that to be 2. Okay? So what does this mean? This means that your small s sub k, this will be less than 2 for all k. Okay, for all k, the set of natural numbers. Okay? And of course, these are all, this S sub k, they are positive, these S sub k's. And furthermore, each term is positive. Therefore, your S sub 1 will be less than S sub 2. Okay? A sub 1 is less than A sub 1 plus A sub 2. Okay? So S sub 1 is less than S sub 2 because, well, A sub 1 will be less than A sub 1 plus A sub 2. And of course, A sub 1 plus A sub 2 will be less than A sub 1 plus A sub 2 plus A sub 3. So this is less than S sub 3, etc. Because again, you are just adding positive numbers from the previous. And therefore, your S sub k is increasing. Okay? So now, you have a sequence, S sub k, which is increasing, meaning it is monotone, and is also bounded. So remember the theorem, monotone and bounded sequence. If you have a sequence which is monotone and bounded, the sequence is convergent. Okay? The monotone convergence theorem. So meaning, limit of S sub k will converge to some number. Okay? And therefore, this guy here, okay, this guy here will also be convergent. So what we actually did here was to show the convergence of this guy by comparing it to a series that we know is convergent. Okay? So you see what the process here is. We are going to compare one series, okay, the series that we want to study, with another series. Okay? In this case, we compared the series we want to study with with somewhat smaller series. Okay? Or with somewhat greater than a bigger series. In this case, this series here, it's less than this series. Okay? The series here, it's less than this series because of this. So what happened here? We have a series, okay? We are studying a series, and we found a series that is greater than the series we are studying. And we know that the series we are comparing this with is convergent. Okay? Then we conclude that the series we are studying is also convergent. So if a bigger series is convergent, definitely the smaller series will also be convergent. That's what we have in this. Okay? This is the one we are studying. We know that the bigger series is convergent. Then the one we are studying must also be convergent. Okay? So, this is the first comparison test. Suppose we have two series here, sum an and sum bn. These are series with non-negative terms. Non-negative terms. Then, if if a sub n is less than or equal to b sub n for all n, okay, and b sub n is convergent, okay, and I mean the series b sub n is convergent, then the series an is also convergent. Okay, so again, we have two series, series an and series bn. They have non-negative terms. Okay, if the smaller series that's the one we are studying. Okay, now if the bigger series is convergent, then the smaller series is also convergent. Okay, now let's have the other side of this comparison test. Okay, the other side of the comparison test is this. Suppose you have now your an to be greater than or equal to bn for all n. And then the series bn is divergent. Okay? Then the series an is also divergent. Okay? So what is this? You have still two series, okay, with non-negative terms, and you want to study this series an, okay, but you found a smaller series, okay, a smaller series relative to the one you are studying. So you found a smaller series that is divergent. Then, of course, the bigger series will also diverge. Okay? So if a smaller series is divergent, of course, the bigger series will also be divergent. Take note, the terms of our series, they are all non-negative. So if you just add, okay, if you just add the terms and you have a divergent series, it will go to plus infinity. Okay? It will go to plus infinity. So if the smaller series goes to plus infinity, what more the larger series? It will also go to plus infinity. Okay? So these are the two parts of your comparison test. So again, two series, non-negative terms. If the bigger series is convergent, then the smaller series is convergent. If the smaller series is divergent, then the bigger series is also divergent. Okay? Questions so far? Now, in order to use comparison tests, you should know a lot of series. Okay? You should know, you should have a big database of known series. Series that you know whether it is convergent or divergent. For us, we have the geometric series, we have the P series, and we actually have the harmonic series. Well, harmonic series is just a P series. So we can use these types of series. So if we are going to analyze a certain series, okay, we can compare it to a geometric or to a P series, then maybe we can find the convergence or divergence of the series we are analyzing. Okay? Example, determine whether the series sum 4 over 3n cubed plus 2n plus 1 and running from 1 up to plus infinity converges or diverges. Okay? Let's see. Solution. We know that for all n, 3n cubed is less than 3n cubed plus 2n plus 1. Correct? We know that for all n, 3n cubed is less than 3n cubed plus 2n plus 1. And they are all positive. By the way, let's write for all n in the set of natural numbers. Okay? For all n in the set of natural numbers. So, we have 1 over 3n cubed plus 2n plus 1. This will also be less than 1 over 3n cubed. And in fact, if we multiply this by 4, the inequality will not change. Okay? Thus, since the series 4 over 3n cubed and from 1 up to plus infinity, you can rewrite this as 4 over 3. You can factor out that constant. Series 1 over n cubed and from 1 up to plus infinity. Since this guy here is convergent, let's write the reasoning. This is convergent. It's a P series with P equals 3 greater than 1. Okay? It's a P series with P equals 3, which is greater than 1. Your constant, it doesn't affect the convergence. So let's just say this part here. Let's just give the conclusion for this. Since this guy is convergent, the series, the original series, 4 over 3n cubed plus 2n plus 1, and from 1 up to plus infinity, is also convergent by comparison test. Comparison test. And that's it. We now have the conclusion. Okay? Very easy to use. Comparison test. It's very easy to use. If you know which series you will use to compare your original series with. Okay? Next example. Determine whether the series sum ln n, well, ln n over n converges or diverges. Okay? By the way, in here, the series ln n over n, and from 1 up to plus infinity, this is series ln n over n, and starting from 2 to plus infinity. Okay? Since, well, ln of 1, this is equal to 0. So we can start at n equals 2. Okay? Okay? So let's try to solve this. For all integer n greater than or equal to 3, okay? For all integer n greater than or equal to 3, ln n, this is greater than 1. If you compute for ln of 2, okay, if you compute for ln of 2, it is less than 1. Okay? ln of 2, that's less than 1. So we start with ln of 3. Okay? We know, well, I hope you know that starting from n equals 3, ln of n will be greater than 1. Just look at, just try to recall the graph of ln function. It's something like this. Okay? If this were 1, if this is the value 1, this guy here, this is E. E, it's 2, it's approximately 2.718. So 2, so this is 1, this is somewhere here, it's 2. I think, yeah, the graph is not really that accurate, but 2, it's somewhere here, okay? So 2, it's somewhere here, and 3, it's somewhere here. So you can start with 3. So if this were 3, okay, the value of ln, it's greater than 1. Okay? So what if we have that? This means that, so 1 over n will be less than ln n over n for all n greater than or equal to 3. Okay? We know that the harmonic series, we know that the harmonic series 1 over n and from 1 up to plus infinity is divergent. So even if you start with n equals 3, well, 1 plus 1 half, they're just numbers. It's a fixed number, 1 plus 1 half. So you can start your series at n equals 3, and the conclusion will still be the same. Okay? So we know that this guy here, okay, is divergent. Okay? This guy here, it's divergent. And so is your series 1 over n and starting from 3 to plus infinity. Okay? Is divergent. Then the series 1 over n and from 3 to plus infinity is also divergent. Thus, again, by comparison test, the series starting from 3 to plus infinity of ln n over n is also divergent. And therefore, even if you start from 2, the series will also be divergent. Therefore, the series starting from 2 to plus infinity of ln n over n is also divergent. Okay? So what we did here is you have two series. You have two series in here. This series here and this series here with non-negative terms. You know that the bigger series is convergent, then the smaller series will also be convergent. Okay? And we know if the smaller series is divergent, then the bigger series will also be divergent. But what if the roles reversed? What if the roles reversed? What I mean here is, what if this guy here divergent? The bigger series is divergent. Can we conclude anything on the smaller series using this comparison test? This guy here, it will be a question mark. And similarly, what if the smaller series is convergent? What about the bigger series? So can we give a conclusion? Using only this comparison test, we cannot conclude anything. Okay? We cannot conclude anything. So we will need another test or another method. Okay? Let us consider this series here. 1 over n squared minus 1. Take note, Here, your series starts with n equals 2. Because when n equals 1, it's, it does not exist. There will be a zero denominator. Okay? So notice that for all n greater than or equal to 2, we have the following. 1 over n squared is less than 1 over n squared minus 1. Okay? If you don't see that, you start with this. Of course, n squared minus 1 will be less than n squared. You have n squared and then you subtract something. It becomes less. So take note, we are starting with n equals 2. So if you get, these are all positive. So if you get the reciprocal, this will be retained. This will be retained. I mean, the inequality changes if you do the reciprocal. So we will have these guys here. Okay? Now, we know that this is convergent. Again, we've seen that. We've proved that. Right? I think, have we proven that? Actually, we proved that because of the P series. But I will show you a nice way of proving this series here. But anyway, we have this situation. The smaller series here, it's convergent, but we will not know using comparison test the convergence of the bigger series. The comparison test cannot be used. Okay? So, what do? We will use the following tests. It's called the limit comparison test. Okay? So, the limit comparison test is the following. Suppose you have two series, series AN and series BN with positive terms. We don't want zero in the terms. If there's zero, just remove that and then renumber the terms. Now, if the limit of AN over BN equals a constancy for some positive constancy, then both series converge or both diverge. Okay? Again, you have a series, or actually you have two series, series AN and series BN. Both have positive terms. Term by term, you get the ratio AN over BN. So you get the ratio AN over BN. You get the limit of that AN over BN as n approaches infinity. If it is equal to a positive constant, take note of this, positive constant, then you have the same conclusion for these two series. They both converge or they both diverge. Okay? Okay? Now, this is for positive constant limit. Okay? This is the one I always use. Okay? But what if the limit is not a positive constant? What if the limit is equal to 0 or to infinity? Okay? Then this will be helpful. Okay? So suppose you have the two series, okay? Series AN, series BN with positive terms. Suppose the limit of the ratio AN over BN as n approaches infinity equals 0. Okay? And then the series for the denominator converges. Then the series for the numerator also converges. Okay? So if the limit of AN over BN is equal to 0, and the series for the denominator here converges, then the series for the numerator also converges. If the limit AN over BN is infinity, okay, and the series for the denominator diverges, then the series for the numerator also diverges. Okay? So you have the ratio AN over BN, and the limit is equal to plus infinity. If the series for the denominator diverges, then the series for the numerator also diverges. Okay? Now, personally, I don't use this. Okay? Personally, I don't use this. The reason is sometimes I am confused. You see, you have to know what the denominator is, and then you need to know what the convergence or divergence of the series denominator. Okay? And then you would know the series for the numerator. Sometimes I interchange them. And of course, if I interchange them, that would be wrong. So I rarely use this guy here. So this is my last resort if I want to know the convergence or divergence of a certain series. But this guy here, this is really, really, really helpful. So you have to know this by heart. So let's try this limit comparison test. So we want to show that this series here is convergent, the series 1 over n squared minus 1, and starting from 2 to plus infinity. Okay? So solution, compare with the series 1 over n squared. You can start from 2 here. Anyway, for this, we are starting from 2. So you can start with 2. Compare with this, which is convergent. Take note of that, which is convergent because it's a P series with P equals 2 greater than 1. Take note when you say something is convergent or divergent, you have to state the reason. That's why in every solution that you will see from me with this in these topics series, you always see I am giving the reason why. Okay? So we want to compare this series here with this series. So you can have this and have this. You can say this is your BN or this is your AN. So this guy here is your AN, this guy here is your BN. But it doesn't matter. Okay? The limit of 1 over n squared divided by 1 over n squared minus 1 n approaches plus infinity. This is simply the limit n approaches plus infinity of n squared minus 1 over n squared. Or this is just the limit as n approaches plus infinity of 1 minus 1 over n squared. And this is equal to 1, which is positive. Okay? So, the limit is positive constant. And since this guy here is convergent, the series we are studying is also convergent. So, by limit comparison test, okay, the series 1 over n squared minus 1 and from 2 to plus infinity is also convergent. And that's it. Next example. Determine whether this series converges or diverges. So you have the series sum 3n cubed plus 4n over square root of n to the 7 minus 4. And starting from 2 to plus infinity. Okay? Now, listen. In this solution, I will give you a hint or a technique on how to choose the series you want to use for comparison. Okay? If you just have algebraic expressions in the numerator and denominator, it will be easy. Okay? Solution. Compare the original series with the following. You look at the numerator, you get the highest term. In a sense, the term that contributes the largest. In here, it's 3n cubed. You put also that in the numerator. On the denominator, you do the same thing. You do the same thing. You get the term that contributes the largest. Here you have n to the 7 minus 4. Of course, this 4, it's just constant. Okay? So you use this n to the 7. But since there is a square root here, you also include that square root. So square root of n to the 7. And then, of course, this is just the series starts from 2 to plus infinity. And then you simplify this. The series n from 2 to plus infinity, you have 3 to the n cubed divided by n raised to 7 halves, correct? And what is this? If you simplify this further, you will have 3 in the numerator. On the denominator, you just n raised to 1 half. Okay? 7 halves minus 3, that's 1 half. So 7 over 2 minus 6 over 2, that's 1 over 2. Now, this series, the series, you have that 3 over n raised to 1 half, and from 2 to plus infinity, this is divergent. Because again, it's a P series, but P equals 1/2, which is less than 1. Okay? Now, let's do the limit comparison test. Now, limit as n approaches plus infinity, we have here 3 to the n cubed plus 4n divided by square root of n to the 7 minus 4 divided by this guy here. So I'll just multiply by the reciprocal. So times square root of n to the 7 over 3 n raised to 3. Is that okay? If you don't see that, let me write it. Let me write the complex fraction. So you have this, and then square root of n to the 7 minus 4 all over 3 to the n, 3n to the cube over square root of n to the 7. So by definition of your division, you will end up with this expression. But anyway, if we compute for this limit, we have, so equals, as n approaches infinity, so we take the limit as n approaches infinity, you can combine this into a single fraction, and then this guy here to another fraction. So you will have 3n cubed plus 4n divided by 3n cubed times, if you combine these two guys here, you can put them in a single radical. So you will just have square root of n to the 7 over n to the 7 minus 4. But you see, as n approaches infinity, look at this. Polynomial over polynomial, same degree. So we just use the coefficients. Similarly for this, polynomial over polynomial, same degree. So we just use the coefficients. And then you take the square root. So this is just equal to 1. And again, this is greater than 0. So by limit comparison test, the original series, 3n cubed plus 4n over square root of n to the 7 minus 4, and from 2 to plus infinity is divergent. Okay? And that's it. Next problem here. Determine whether the series converges or diverges. So you have series arctan divided by n raised to 1/2 minus 4. Okay? Arctan over n raised to 1/2 minus 4. You sum that from n equals 17 up to plus infinity. So for this, we recall the following. Again, graph of your arctan. This is pi over 2, and then it's something like this. Okay? And furthermore, you have here, this is 1. This occurs at pi over 4. Sorry, it's the reverse. Okay? This is this guy here, it's pi over 4. It occurs at n equals 1. Okay? Okay? So solution. For all n greater than for all n greater than 1, in fact, we have 17 there. Okay? So we start with 17. For all n greater than or equal to 17, the value of arctan, it's somewhere here already. It's above pi over 4. So you have pi over 4 less than arctan of n. Okay? Which means, so, pi over 4 over n raised to 1/2 minus 4, this is less than arctan of n divided by n raised to 1/2 minus 4. So what we're going to do, we study this. We show that this is divergent. By comparison test, this will be divergent. But to show that this is divergent, we will use limit comparison test. Okay? So consider the series pi over 4 divided by n raised to 1/2 minus 4, and starting from 17 up to plus infinity. Compare it with the series 1 over n raised to 1/2, and n starts from 17 up to plus infinity. Okay? This is divergent. So which is divergent? Because it's a p series with p equals 1/2, which is divergent. Okay? P series p equals 1/2, less than 1. Okay? So limit 1 over n raised to 1/2 divided by pi over 4 all over n raised to 1/2 minus 4, n approaches plus infinity. So this is just the limit n approaches plus infinity of n raised to 1/2 minus 4 divided by pi over 4 n raised to 1/2. And if you get the limit of this, you'll just get 4 over pi. And this is again a positive number. So the series pi over 4 over n raised to 1 half minus 4, and from 17 up to plus infinity is divergent by limit comparison test. Therefore, the series arctan n over n raised to 1 half minus 4, and from 17 up to plus infinity, this is also divergent by comparison test. Okay? So notice how I used different tests just to prove the convergence or divergence of our original series. You don't have to do this, okay? You can just immediately compare this guy here to this guy and just use limit comparison test. In our computation, this guy here will just be arctan. And as n approaches infinity, your arctan will go to pi over 2. So you will have a different limit in here. But it's still a positive number. So you don't have to do this part here. This part here. So this guy here, you can immediately replace it by this. That is, again, if you use this and compare it directly to this. Okay? But in this example, I just want to show you that sometimes you will have to use different tests just to have a conclusion on your original series. You will see later in the course, you will have to use several tests. In fact, we have been using that. It's immediate to us. We use the p-series test. And then we use the comparison test or the limit comparison test. But there will be times you will have to use a lot of tests before you will get your conclusion. A chain of tests. Okay? Next example here. Determine whether the series e to the n plus 3 over square root of n e to the n minus 1 and from 1 up to plus infinity converges or diverges. Okay? So, solution. Like I mentioned earlier, you use the term that contributes more in the numerator and in the denominator. And then you will have a series where you can compare the original series with. So just compare with the series. In the numerator, e to the n contributes the greatest. The denominator, you use square root of n e to the n. That's a product here. So you also use that product. And then here, n from 1 up to plus infinity. Okay? And then what is this? Let us simplify this. The series, so e to the n over square root of n, and then e raised to n over 2. Square root of e to the n, it's e to the n over 2. So n from 1 up to plus infinity. And this guy here, you have e to the n over 2 divided by square root of n from 1 up to plus infinity. Okay? So let us do this. Okay. Now, for all for all n greater than or equal to 1, 1 is less than e raised to 1 over n. E raised to n over 2. Okay? So for all n greater than or equal to 1, 1 is less than e raised to n over 2. Agree? Well, if you look at the exponential function or the graph of the exponential function, it will be something like this. This is 1 here. Okay? So this is 1 on this part. Okay? So this is 1 here. If n equals 1 in here, it's greater than 1. So you know that 1 is less than e raised to n over 2. So I have here 1 over square root of n. This is less than e raised to n over 2 over square root of n. Now, the series, now, the series 1 over square root of n, and from 1 up to plus infinity, this series is divergent. Again, reason it's a p series with p equals 1/2, which is less than 1. So, by comparison test, the series e raised to n over 2 over square root of n, and from 1 up to plus infinity, this is also divergent. Okay? Now, let us look at the limit. Next, we find the limit of what is our original series there. It's e to the n plus 3 over square root of n e to the n minus 1 times square root of, let me use this guy again. Let me use this guy again. So square root of n e to the n divided by e to the n. Here we get the limit as n approaches plus infinity. So we will have limit as n approaches plus infinity e to the n plus 3 divided by e to the n. And then you will have square root of n e to the n over n e to the n minus 1. Okay? Then let us just analyze this. In fact, you will get limit equals 1. But let us show some more details. Limit as n approaches infinity, quantity. You will have here 1 plus 3 over e to the n. I think I will need more space in here. And then inside the square root, you will have something 1 plus 1 over n e to the n minus 1. Okay?
Sir, why would it be 1 over n to the n minus 1?
If you try to combine this into a single fraction, you will end up with this. From here, what you can do is you subtract 1 and then add 1. So subtract 1, add 1, and then you use this part here, you separate. That's your 1. And you will still have this 1 over n e to the n minus 1. Okay? But now, in this form, it is clear. As n approaches infinity, this will go to 0. This will also go to 0. So the limit will be 1. And again, it's a positive number. So by limit comparison test, you have this series here to be convergent. Okay? So let me just write the conclusion there. How do I edit this? So I'll reduce the size so I can fit in the conclusion. Yep. So by limit comparison test, the sum e to the n plus 3 over square root of n e to the n minus 1 and from 1 up to plus infinity is also divergent. Okay.